In this episode, we'll look at the streamflow constraints feature and the associated input file, and we'll do that with the supply to example problem, which also has some new features. It's transient and it has external variables, as we'll see. Starting in the distribution directory for GWM 2005 1-5-2, and going to the doc directory, we'll be looking at the open file report indicated here. Here on page 83 of that report is the supply to problem. This is a valley with a stream running through it, indicated by the gray line. Specified head boundary conditions on top and bottom, producing a sloping condition. The mod flow simulation of this system includes recharge over the domain, and the stream is modeled using the STR package. The system is modeled as one layer, which has transmissivity independent of head. The problem is modeled as transient with 4 seasons over 3 years for a total of 12 stress periods over the course of the simulation. The management problem is to select pumping rates in each stress period over the 3-year time period at the 4 wells so as to maximize withdrawal of water over the simulated period, the volume of water withdrawn, and with constraints on streamflow depletion at these 4 locations. One of the interesting elements of this problem is the way the pumping is allocated to the 4 wells. Well number 1 withdrawals at the same rate, that rate to be determined by GWM, but it will be the same rate in all 12 stress periods. Well 2 has seasonal withdrawal rates. In other words, it will be able to pump at a different rate in winter stress periods, at a different rate in spring stress periods, and so on. Well 3 will only withdraw in year 2 of the simulation, and well 4 only withdrawals in the spring and fall of each year, and in that case at different rates in each season. There is a total demand for water in this system that must be satisfied, and it can be satisfied by either pumping in each season from these wells or from importation of water from an external source. That imported water is more expensive than water withdrawn from these wells, hence it is desirable to minimize that importation. So now let's look at how input is produced for this problem. Returning to the distribution directory, going to the data directory, we find the supply to problem, and there are both the mod flow input files and the GWM input files. And here is the GWM file, and we see the familiar decision variable objective function, variable constraints. We have a summation constraints file here and the new file, the STRMCON. We'll start looking at the first 3 familiar files. And here is the DECVAR file. 2 new features in this. We have we have 7 withdrawal wells, and looking at the first one, Q1, and recalling that was active in all stress periods, we see that the NSP variable, the number of stress periods, the stress period numbers rather, is 1-12. This is a character string read by GWM and is interpreted as being that this well is available and that this decision variable is associated with pumping in all 12 stress periods of the model. In other words, a single value of Q1 will be determined and it will be applied in all 12 stress periods. Q2A is at location Q2, the second well, but is only active in stress periods 1, 5, and 9. So this is the winter season. Q2B is the spring season, summer season, and fall season. Q4 has two decision variables associated with it that operate in the spring and fall seasons respectively. And as you can probably figure out, this notation means that the colon here simply means 1 and 5 and 9, for example. The other new feature here is the introduction of external variables. There are 4 of them in this case. They're given a name, they're given a type, and a stress period in which they are available. External variables have no direct impact on the simulation model. They are active in the management model and indirectly affect simulation through the results of the optimization problem. Glancing briefly at the STRMCON file, we see the withdrawal variables and the external variables, which also require a lower and upper bound. Finally, in the objective function file, we see the coefficients on the the flow variables, the 7 flow variables, and the 4 external variables. And this input file implements this objective function, where the value of withdrawn water is $1 per 1,000 cubic feet. So all the withdrawals have a coefficient as indicated, and the cost of imported water is somewhat more. So the objective is to maximize the withdrawn water, which is cheaper, and minimize the imported water. And here you can see those coefficients assigned in the objective function. And here also is a good example of where the weighted sum of decision variables is useful, because it will multiply the flow rate by the duration of the flow to produce a volume of water, so that the units in the objective function work out. Here's a brief glance at the summation constraint file, where we have 16 summation constraints, and these place upper and lower bounds on the withdrawals in each season, requiring that water supply be satisfied given the various sources in each period. A new feature of this problem is the use of streamflow constraints, and those are imposed at the 4 locations mentioned earlier, which are particular cells where the STR package models a streamflow. And here's the stream constraint file. It's quite similar to the head constraint file in that we have a list of the constraints. We have the constraint name, the segment and reach in which it occurs using the stream package terminology and numbering scheme, and then a requirement that on the direction of the constraint and the value, and then finally the stress period in which the constraint is active. Constraints can be placed on the stream flow directly, and they can also be placed, as is the case here, on stream flow depletion. So what we're requiring is that at the 12 indicated locations, the stream flow be depleted by no more than the indicated value. This implies that there needs to be a base reference run where non-pumping conditions are determined, and and those conditions can then be compared to the conditions computed by under the optimal conditions under the optimal pumping rates to confirm that in fact we meet the constraints. Now, taking a quick look at the output file, we look through we see the decision variables being echoed and note that they are available in certain stress periods as indicated in the input. Also that the external variables are provided along with the stress periods in which they're active. Here's the objective function, minimizing the withdrawals, maximizing the withdrawals, and minimizing the importation. Here are the summation constraints to implement the water supply demand requirements. And here are the stream flow constraints, saying that at this location and segment and reach, the depletion can be no more than a certain amount at the end of stress period indicated. Looking now at the solution, we see that the streamflow depletion constraints are all satisfied initially before any pumping is applied, as we might expect, but the water supply demand constraints are not met. Jumping down to the solution, we see the particular set of withdrawal rates that have been selected. We see the importation rates, and there's some importation required to meet the constraints. And we see what is binding. Streamflow depletion is binding in several locations, not all locations, but some locations.